Hello everyone, this is Professor Roman. Let us continue the field theory lectures. We're ready now to start Chapter 2, Embeddings and their extensions. Ring homomorphisms between fields play a very key role in field theory and Galois theory. Since a field F has no non-trivial proper ideals, any non-zero ring homomorphism, sigma, between two fields has to have a trivial kernel. The kernel is an ideal. It can't be everything, because then the homomorphism would be the zero homomorphism, so it has to be trivial. That means that any ring homomorphism between fields is in fact injective. It's an embedding of the domain into the codomain. So the morphisms of field theory are the ring embeddings. Now let's cover some notation just to make sure we're all on the same page. Let f be a function from a to b. Then the restriction of f to a subset of the domain A is denoted this way. It's a common notation. Occasionally, if the restricted domain is clear, I might not include the vertical bar and the restricted domain, just write f again. This symbol, which is an arrow with a hook on the back, denotes an embedding. So it denotes a ring morphism that is injective. So when you see sigma colon f hook arrow L, you know this is read sigma is an embedding of the field F into the field L. The set of all embeddings from E to L, into L is denoted this way, HOM EL. The set of all automorphisms of E is denoted AUT of E. Okay? Definition, let EL be a field extension. Let sigma be an embedding of E into L. Sigma fixes a subfield F of the domain E if sigma of F is equal to F. Sigma fixes a subfield F of E pointwise if sigma sends every element of F to itself. So this is clearly much more restrictive than just sigma sending the set F to the set F. It can scramble the elements within F, but this one cannot. Let's also recall from the ring theory course that if we have a polynomial, and if sigma is an embedding, then the induced map, sigma, on the polynomial rings is defined by sigma p of x. This is another notation. P superscript sigma of x is what you get by applying sigma to the coefficients of the polynomial. This is also an embedding, but now these are rings rather than fields. If sigma maps a polynomial ring to itself and it fixes the base field pointwise, then it's fixing the coefficients pointwise. And so sigma p of A is p of sigma A, because we also have to apply sigma to the coefficients of the polynomial, but sigma fixes those coefficients. By restricting the codomain of an embedding sigma from F to E to the image of sigma, we get an isomorphism. It is now surjective and therefore an isomorphism. And as a result, embeddings preserve field theoretic properties that involve only the elements of the image of the embedding, because you now have an isomorphism, and so the field theory properties are preserved. So in particular, embeddings preserve factorizations and roots. So if sigma is an embedding of F into L, a polynomial in F square bracket X factors over F if and only its image under the embedding factors over sigma F. And here it is in symbols. An element A in F is a root of P of X if and only if its image, sigma A, is a root of the image polynomial. Again in symbols. And also, the multiplicities of A and sigma A are the same, and that is important. If KF is a field extension and little a is an element of the bigger field F, and it's algebraic over the smaller field K, then the minimal polynomial of A with respect to the field K, if we map that by sigma, we will get the minimal polynomial of sigma A over sigma K. So in particular, if sigma K is equal to K, then A and sigma A have the same minimal polynomial. Embeddings preserve meets and joins. So meet is intersection, join is more complicated, as you know, but this is what that looks like. And so in the particular case of a join or composite of two fields, sigma FE is sigma F composed with sigma E. Embeddings preserve adjoining. So this is F with the set S adjoined. We apply sigma. That is equal to sigma F with the set sigma S adjoined. I'm going to leave this theorem for you to prove. It would be very good practice. In the book itself, I said I'll leave parts 1 and 2 for you, and here's part 3, but I would suggest very strongly you try to prove that yourself. We now come to an important result concerning the linear independence of embeddings. And we're going to need this later on, so in our discussion of solvability by radicals. So let E and F be fields. The set of embeddings of E into L is a vector space over not E but over L under addition of functions and scalar multiplication by elements of the codomain. What we want to show is that any non-empty finite set of embeddings in from E to L is linearly independent over L. This proof that I am about to do for you is very similar to a proof you may have seen, you would have seen if you went through the linear algebra course, but in an ordinary linear algebra class, you probably would have seen it. The proof that eigenvectors associated with distinct eigenvalues are linearly independent vectors. So suppose to the contrary that we have a set, script E, sigma 1 through sigma n, of embeddings from E to L, and that there is a non-trivial linear combination that's equal to 0. So the coefficients alpha I belong to L, but they're not all 0. We want a contradiction. We can assume that this linear combination has the fewest number of terms among all such non-trivial linear combinations that are equal to 0. So in particular, there's got to be at least 2 terms, and none of the coefficients are equal to 0. And the equation, let me bring it back again quickly, this equation then is equivalent to saying that alpha 1 sigma 1 evaluated at B all the way through here is 0 for all little b in E. But as with the eigenvector proof, we can find a shorter linear combination that'll give us our contradiction. What we do is we choose an element A in E for which sigma 1 of A is different from sigma 2 of A. Sigma 1 and sigma 2 are distinct, so there must be some point at which they're different. Multiply this by sigma 1 of A. On the other hand, instead of that, replace B here by AB, and then separate, because the sigmas are morphisms, homomorphisms. And we'll get this equation. Now, if you look carefully, you will see alpha 1 sigma 1a sigma 1b, and also alpha 1 sigma 1a sigma 1b. So the first 2 terms are the same. When we subtract, we get a shorter linear combination. But if you look at this first one, this is non-zero. Okay? Because sigma 1a is different from sigma 1b, sigma 2a, sorry. And so this is non-zero. Alpha 2 is non-zero. So this holds for all b and e. We have our shorter, non-trivial linear combination of the sigmas that is equal to 0. And that contradiction proves that this set E, after all, had to be linearly independent. Forgot the box. Okay. Now, embeddings themselves are only a tiny portion of the story. It is extensions of embeddings that play a major role in our theory. Extension in the sense of one function can be an extension of another, something you're probably familiar with, but let's go over it anyway. As shown in this figure, let sigma be an embedding from F into L. So here's the image of sigma F. It's a subfield of L. And consider an extension, Fe. Then an embedding sigma bar of E into L, for which the restriction of sigma bar to F is sigma, is called an extension of sigma to E. This is not field theory. This is just basic theory of functions. The set of all embeddings of E into L that extends sigma will denote this way. So there's the subscript sigma here. If we have a tower, FEL, then an embedding of E into L that extends the inclusion map is called an embedding of E over L. So if this sigma here is the inclusion map, which means F is got to be a subfield of L, and we extend the inclusion map, we get what is called an embedding of of E over L rather than over sigma. Okay. And this set, so here's the inclusion map J, is denoted with an F, subscript F rather than a subscript J. So this is then the set of all embeddings of E into L that fix F pointwise. This is going to be our major object of study for quite a while. The set of all automorphisms of E over F is denoted this way. So these are the automorphisms of E that fix F pointwise. A couple of basic properties of extensions that I'm leaving for you to prove is that if we have this is an embedding of F into L, but into sigma F it's an isomorphism. And if we have an algebraic extension and then we extend sigma, the images are form an algebraic extension. So this preserves the property of being algebraic. If E is algebraic over F, sigma bar of E is algebraic over sigma of F. This is probably, the stuff about extensions we're talking about now, we'll continue to talk about, may be new to you, probably is new to you. It's going to take a little effort. One thing that I think would tend to be confusing is that the word extension is being used in two different ways. We've been talking about field extensions for some time, but now we're also talking about extensions of embeddings. So the word extension now can be either a field extension or an embedding extension, and the context is going to have to help separate that sometimes, okay, help us understand what the word means. Extensions also preserve algebraic closures. So if they preserve the property of being algebraically closed, and so since they also preserve the property of being algebraic, they preserve the property of being an algebraic closure. Okay. So I'm going to let you ponder that because I think it's critically important for you to spend some time dealing with these concepts before they become overwhelming. Embeddings are related to automorphisms. Suppose that Fe is an algebraic extension. And embedding, as we at least discussed, maps roots to roots. And because every element of E being an algebraic extension, is the root of some polynomial over F, and it follows that any embedding of E into itself over F, so it's fixing the base field pointwise, is actually surjective. It's an automorphism of E. Let's look at that more carefully. That's not a proof. Just a statement that the proof is, the theorem is coming. If alpha is in E, then sigma maps the set of roots R sub E of the minimal polynomial of alpha that lie in E to itself. A root goes to a root. Okay. Sigma is an embedding of E into itself. So it sends a root to a root, but the root is also in E, therefore it sends the elements of RE to themselves. I'm not saying pointwise. It looks like this. Sigma RE is contained in RE. But sigma is injective and RE is finite. So in fact, we have equality here. In other words, sigma permutes these sets of roots. I'm not saying that R sub E is all the roots of the minimal polynomial of alpha. It's all the roots of minimal polynomial that lie in E. So sigma is a permutation of that portion of the complete root set. But that shows that sigma itself is surjective. Every element of E is in a root set and therefore is the image of some other root under sigma. So sigma is an automorphism of E. If Fe is algebraic, the embeddings of E into itself over F are actually all of those are surjective, so they're the automorphisms of E over F. Okay, now one important, when you think about extensions of embeddings, you are extending the domain, and when the extension of the domain has the special property that it's algebraic, the embeddings of E into itself are automorphisms. But we're also going to be very interested in the embeddings of E into E bar, an algebraic closure of E, again over F, fixing the base field pointwise. These need not be automorphisms. If I replace the second E here by E bar, and that's a set we're going to be very interested in, we lose this. Okay. When we don't lose this, when the embeddings of E into E bar are the same as the automorphisms of E, that kind of extension of the domain is very special. And it is called a normal extension. And we'll have a great deal to say about normal extensions later in this chapter and in the rest of the course. For example, we'll discover that an extension is normal, algebraic extension is normal if and only if it's the splitting field extension for a family of polynomials. So that's an interesting connection because we're talking about embeddings here and we're talking about splitting fields of polynomials, and they're connected. Let us now address the issue of the existence of extensions. I've defined for you what extensions are, and we've looked at some of their properties, but we have not yet addressed the question of whether you can extend any embedding to a larger domain, or how you would do that. So, as we will see, extensions of embeddings have a remarkable property. Namely, if sigma is an embedding of F into L, and L is algebraically closed, in our discussion, the codomain will always be, I think, always be algebraically closed. And if Fe is an algebraic extension of the domain F, then the cardinality of the set of all extensions of sigma to the bigger domain E doesn't depend on sigma. Now, of course, the set of extensions will depend on sigma, but we're talking about the cardinality of that set. That is independent of sigma. It depends only on the extension FE, the extension of the domain. So to put it differently, all embeddings sigma of F into L, where L is algebraically closed, have the same number of extensions to the larger domain E. We're going to prove this in steps. First for finite extensions, first for simple finite extensions, then for arbitrary finite extensions, and finally for all algebraic extensions. And to begin, we would like some terminology. An extension FE has a separable degree if the cardinality of this set of extensions of sigma to E, again, L is algebraically closed, is the same for all embeddings, and thus depends only on the extension and not on sigma. So here it is said differently. If tau is another embedding, so we have sigma embedding F into L and tau embedding F into L prime. L prime is also algebraically closed. Then these two sets of extensions have the same cardinality. And in this case, we denote the separable degree of the extension by this. It looks just like the notation for the vector space degree, the vector space dimension, but I put sub S for separable. So this is read the separable degree of E over F, and it is this cardinality. Again, assuming that this is independent of sigma. The notation here has sigma on this side, but not on this side, so that's critical. The extension FE must have a separable degree, and then it is this quantity. And as I mentioned a minute ago, we're going to show that all algebraic extensions have a separable degree, which may certainly be infinite, and we'll look at the properties of separable degree. You probably can guess that from the terminology that separable degree has something to do with the separability of the extension. Now here is a key fact that we will use for our upcoming discussion. If each step in a tower has a separable degree, then so does the full extension. Moreover, the separable degree is multiplicative, so the separable degree of the full extension is the product of the separable degrees of each individual step in the tower. And to prove this, it is sufficient to prove the result for towers of length 2. I'll let you ponder why that is. So let sigma be an embedding of F into L, again, L algebraically closed, and let S be the set of ordered pairs, sigma 1, sigma 2. Sigma 1 is an extension of sigma to the intermediate field K into the same codomain L. And sigma 2 is an extension of sigma 1 to the domain E. So it's a two-step process. First extend sigma to K, then extend the result to E. We are assuming that each step in this tower has a separable degree. And so the cardinality of this set S of ordered pairs is the, well, in any case, it would be the cardinality of this set times the cardinality of this set. But because we're assuming each step has a separable degree, those cardinalities are equal to the separable degrees. So the cardinality of S is the product of the two separable degrees from the two steps in the tower. Now, notice that sigma 1 extends sigma to k, sigma 2 extends sigma 1, so sigma 2 is also extending sigma. So sigma 2, in fact, belongs to this set of extensions, all the way, extensions of sigma all the way to E. Moreover, each ordered pair in S has a distinct second component. And I'll let you ponder what would happen if you had two ordered pairs with the same second component. Why would the first components have to be the same as well? Therefore, the product of these two separable degrees, that's the cardinality of S, is less than or equal to the cardinality of the set of all extensions. On the other hand, every extension of sigma to E is the second component of a unique ordered pair in S. You just restrict tau here to K, and you'll get an extension of sigma to K. And so we have this inequality as well. So we have the two inequalities, and therefore the cardinalities are the same. And so the cardinality of this set, which is the cardinality of S, is the product of these two. And this is independent of sigma. And that shows that the extension Fe has a separable degree. The reason it does, the definition of that, is that this thing is independent of sigma. And since it's equal to this the product here, there's no dependence on sigma on the right side here. And so we can say that this is now equal to this separable degree, and we have our final result. Okay? Don't worry if it's a little confusing. That happens to most of us when we first see this. It takes a little persistence and to get comfortable with it. Okay. So, this fact, and it's so important, let's look at it again. If we have a tower of fields, and if each step has a separable degree, meaning that the extensions for each step, the cardinality of the set of extensions doesn't depend on what you're extending, then the full extension has that same property, and you can get the separable degree of the full extension as a product of the separable degrees of the steps. And this is our key tool for understanding how extensions work. So we'll begin with the case of simple extensions. I should really add, these are simple finite extensions, not transcendental. That wouldn't work at all. Okay, so we'll begin with this case. F extended to F with alpha adjoined. Simple algebraic extension. So we'll let sigma be an embedding of F into L, where L is algebraically closed. Now in this case, we know precisely what the extensions, say sigma bar, of sigma look like, because we're extending to F with alpha adjoined An extension is completely determined by what it does to alpha. Moreover, sigma bar of alpha has to be a root of the image of the minimal polynomial of alpha. Roots have to go to roots. And alpha, being algebraic, has a minimal polynomial. It's a root of that minimal polynomial, so sigma has to send alpha to a root of the image of the minimal polynomial. Also, each root beta of this image of the minimal polynomial, now we're in L here, which is algebraically closed, so this polynomial splits. There is an extension for each root of this polynomial in L. There is an extension of sigma. I'm calling it sigma alpha beta because it's defined essentially by mapping alpha to beta. So sigma alpha beta, since in a polynomial in alpha, you take the image of the polynomial and replace x by beta. And this definition is for all polynomials p of x whose degree is less than the degree of the minimal polynomial. This gives us well-definedness. Okay. We have to be a little careful because if we consider all polynomials p of x, and there would be different polynomials would have the same value, p of alpha. And so we'd have to make sure it was the same on this side as well. So by restricting the polynomials to those of degree less than that of the minimal polynomial, we don't have to spend time showing this is well defined. And I'm going to leave it for you if you want to fill in the details of why this is well defined. It's right here. And also, I'm going to leave it for you to show that this is a ring homomorphism. And also that it is injective. It's a one-liner. So sigma alpha beta is indeed an extension. It's an embedding of F with alpha joined into L. It's an extension of sigma to this larger domain. It follows that there is exactly one extension of sigma for each distinct root of this polynomial. This is the image under sigma of the minimal polynomial of alpha. But this polynomial and the minimal polynomial of alpha have the same number of distinct roots, same multiplicity. So there's exactly one extension of sigma for each distinct root of its minimal polynomial. And here is the theorem. We have a simple finite extension, or equivalently simple algebraic extension. Now let sigma be an embedding of F into L, L algebraically closed. If beta is a root of the image polynomial, the image of the minimal polynomial, then sigma can be extended to a unique embedding, and that covers all possible extensions. So the number of extensions is equal to the number of distinct roots of this minimal polynomial. That has nothing to do with sigma. It has to do only with alpha, with the extension F extended to F with alpha joined. So finite simple extensions have a separable degree, and it is equal to the number of distinct roots of the minimal polynomial of alpha. Therefore, the separable degree is either equal to the ordinary degree, the vector space dimension, if alpha is separable. Alpha separable means its minimal polynomial is separable, which means it has no multiple roots. They're all simple roots, which means the number of roots is the degree of the polynomial, which is the dimension of this extension. But you may recall that when alpha is inseparable, the field must have non-zero characteristic P, a prime characteristic P, and every root has the same multiplicity, and that is P to the D, where D is called the radical exponent of the polynomial. And so the number of distinct roots is the degree of the polynomial divided by P to the D. You may have to go back and research that if you want, or look it up on the internet. But frankly, what's important about that is simply that the separable degree divides the ordinary degree in both cases. And that's what we'll concentrate on. In view of the earlier theorem, we now can say that the separable degree for finite simple extensions is multiplicative. If we have a simple tower, and you remember what that means is that the word simple then applies to each step. It's a tower in which each step is simple. The full extension is not simple, necessarily. It could be. But if each step is simple, we call it a simple tower, then the full extension has a separable degree, even if it's not simple itself. And we have this product, the multiplicativity. So that is the story for finite simple extensions. In theory, we know how to get all the extensions. I say in theory because you have to find the roots of a certain polynomial, but we know exactly what they look like, and we know exactly how many there are. Because of this, primarily, I'm going to make a non-standard definition. It's very useful, but you probably won't see it elsewhere. A finite extension, Fe, that has this property that its separable degree, so it has to exist, is equal to its degree, I'm going to refer to that extension as degree-wise separable. It's not a standard term, as I say, but I find it useful. Let us now examine extensions in the finite case, finite extensions of the domain. Frankly, there's not much to do because we can leverage the results on finite simple extensions. Any finite extension Fe can be decomposed into a simple tower, a tower of simple extensions. And so the theorem we just discussed gives us the following. Let Fe be a finite extension. Any embedding sigma of F into L algebraically closed, can be extended to an embedding of E into L. Moreover, if an element alpha in E has this minimal polynomial, and if beta is a root of the image polynomial, then we can choose sigma bar, our extension, to map alpha to beta. The class of finite extensions has separable degree, it's multiplicative, and the separable degree divides the full degree. And finally, the class of degree-wise separable extensions has the tower property. As to part 1, we already know that sigma can be extended to sigma with alpha adjoined. We've chosen, there's two statements here, we're doing them both at the same time, so we have an alpha in E. We can bump up sigma to the domain to F with alpha adjoined, and that'll give us this map we're calling sigma sub alpha beta, and that can be further extended one step at a time through the tower because of the previous results, and that'll give us an extension of E to L. You could specify more values along the way. I didn't go into that. It'd be a little tedious to write it all down, and we don't need it. But each time you do an extension through the domain that's a simple extension, you can specify some information about what goes to what. Okay. As far as part 2 is concerned, we decompose the finite extension into a simple tower. We have multiplicativity of both the degree and the separable degree. And we have the fact that the separable degree divides the ordinary degree. And so the separable degree of the full extension is the product of the separable degrees of the individual steps, and that divides the product of the ordinary degrees of the simple steps, which is the degree of E over F. Okay, and for part 3, if we have a 2 tower that's finite, where part 3 was the class of the class of degree-wise separable extensions has the tower property. So if we have a finite extension here, both types of degrees are multiplicative, so we have this statement for the ordinary degree and for the separable degree, but each separable degree divides the full degree, and so the separable degree EF is degree-wise separable if and only if each step is degree-wise separable. And that's the tower property.